Hello everyone, we're going to be continuing our study of vector-valued functions, and we're actually going to do calculus this time. So let's remind ourselves the definition of a derivative, the limit definition of a derivative that we learned in Calc 1. So first we'll start with like where it comes from. So if you have like some kind of curve, and then you wanted like the derivative between here, or yeah, sure, the derivative here, right? The slope of this at this point, and then this point right here was at t, right? And then this right here was f of t. So then you take another arbitrary point, let's say h over here, or well, this is going to be t plus h. That means, oops, this is going to be f of t plus h. We could write our traditional, and we wanted to find like the slope of a line that passes through these points. So the slope of this line, you would just do f of t plus h minus f of t over t plus h minus t, which is just h. And then you would take the limit as h approaches 0. And what h is its change in t. Okay? And then on the top, this is change in f. As it gets really, really small, this is, well, as this change gets really small, it's just a small change in f over small change in t, right? Now, luckily for us, this kind of definition extends itself to vector-valued functions. So stuff that looks like this. Yeah, well, actually, let's just deal with the first two inputs, okay? Stuff that looks like this can be written, like their derivative can be written very similarly. And what that really looks like is if you have some, okay, maybe not like that. Well, actually, sure. Say you have some kind of vector-valued function, right? Then you wanted a slope, a tangent vector right here. You would look at this vector, and you would look at, you would look at that vector. Okay, so say this is r of t. This guy is r of t plus h. Then their difference is going to give you this vector, right? Oops. Their difference is going to give you that displacement vector. That's just r of t plus h minus r of t. That's that vector right there. And then this is like synonymous with the delta f part up here. This is a change in f. So this is like change in r as a vector, right? If you want change in t, that's going to be this next part. Well, that's just t plus h minus t, which is just h, right? So this is just h. And then as you take the limit of this guy approaching 0 for r of t plus h minus r of t, that's going to be equal to your r prime of t. Okay? And what you could, I mean, this just tells you that this kind of definition applies to this. If you apply this to a vector-valued function, you just get this. It's going to be the limit h approaches 0 for, so remember the first slot is our x of t. t plus h minus x of t over h, comma, right? And then I'll do that for whatever variables you have, and that's it. And then this is just, this is quite literally just x prime of t, comma y prime of t, and then whatever, you just, so that just tells us that the derivative of a vector valued function as a whole is the derivative of each of its components with respect to t. So, oh yeah, and then we also have another character to introduce, that being the unit tangent vector. It's written like this. This guy's important, and he's going to be used later because typically when we take the vectors that come out of this derivative function have length. And sometimes we only want to just use the directional part. We want to give them a direction. So that's what this unit tangent vector's purpose is. And the way you just find that is you just do r prime of t over the magnitude of r prime of t at a certain t value. This is a general expression for a given r of t. It's going to change with every t value, right? With whatever t value you're at. So let's look at an example from last lecture. Let's say r of t equals t cosine t, t sine t, t. This is just the spiral, remember? It like spirals up the z-axis, kind of like that. So his tangent vector is just going to be minus t sine, well, you're going to have a product rule here, so it's just going to be cosine t minus, I'm being really stupid, aren't I? I haven't taken derivatives since linear algebra. But anyway, okay, so that's cosine t, and then this is going to be minus t sine t, right? Because you take the derivative of this guy times that, that's just cosine t, then plus the derivative of this guy times that. So that's that. Second part is just going to be sine t plus t cosine t, and then this is just 1, right? And then if you want to take the magnitude of this guy, it's kind of a hassle, but here we'll just do it in a moment. So the magnitude of this guy is just going to be the root of this guy squared plus this guy squared plus this guy squared. So this is that guy squared, and then this guy squared is going to be cosine squared t plus, or I guess be minus t sine t cosine t. And you're going to have 2 of these, and then plus t squared sine squared t. This guy squared is going to be plus sine squared t. Is going to be plus 2t sine t cosine t plus t squared cosine t. Right? So then this cancels out with this, and you get this cosine squared, and then this sine squared give you another 1. And then from these 2 t squared, from this guy, and from this guy, this is a t squared sine t, this is a t squared cosine t, you're going to get a t squared. because you could factor out a t squared and you use your Pythagorean. So you get the magnitude is going to be t squared plus 2. So your unit tangent vector is just going to be this guy, cosine t minus t sine t, comma, sine t plus t cosine t, comma 1, all over root t squared plus 2. And then say we wanted this for a certain value of t, then you would just plug that in, and that would be your answer. So, I don't know, say 0, you would get, so therefore, the tangent vector evaluated at 0 is just going to be, it's going to be over root 2, and then you're going to have 1, 0, 1, 1, 0, 1. Okay. So yeah. Now, one important thing to note is that the derivatives, like I guess for, let's move this camera, okay. The derivatives of certain vector products, so the cross product and the dot product, are pretty similar to the, what do you call it? Just the normal product rule. So if you have like u dot v, and you wanted to take the derivative of this guy, then you're going to get u prime dot v plus u dot v prime. And then if you wanted to do the same thing for a cross product, this one, the order matters. You want to keep it in this order. So you're going to have u prime cross v plus u cross v prime, right? Another cool thing about these is that integrals are pretty much the same thing. So if you have an indefinite integral of like an r prime of t, then you're going to get an r of t plus, remember this is an indefinite integral, so you get a constant, but this constant is a vector. So that just means that if you really wanted to analyze this, it's going to be like, so if first you had x prime of t, comma, y prime of t, and then you integrated this guy with respect to t, then you're just going to get x of t plus a constant that's for the x variable, comma, y of t plus a constant that's for the y, right? And the constant vector that I'm talking about here is just this, cx, comma, cy. That's what I mean when I say a constant vector. And then if you have a definite integral, so if you're going from like a to b of r prime of t, then this is just r of a minus r of b. This is like a displacement vector between, what do you call it? It's like, yeah, this is a displacement vector between r valued at point A, r valued at point B, and that's equivalent to summing up all these little r prime of t's from A to B. So, yeah. And then next section is just motion in space. So the relevance of these guys pertaining to like motion, like how you saw in Calc 1, like acceleration, or velocity and whatever. Oh, also, yeah, for this one, it's like if you have an R of t, and then you have this is R at A, R of A, this is like R at B. And if you sum up the tangent vectors, like infinitely many tangent vectors from A to B, then you're just going to get this displacement vector right there. Right? Just R of A minus R of B is what that means. But yeah, now motion in space, it's like how you had, how in like Calc 1 they'd give you a position function, I think. They would call it, what was it, like S of t? So if they give you S of t, they tell you that S prime of t is just a velocity function, v of t, and then v prime of t is acceleration, right? Same thing here. They're going to give you some R of t. This is a position. It just tells you where you are. And then R prime of t is velocity. And then, oops, not v prime. And then v prime of t is acceleration. And magnitude of v of t is it's just speed, right? So this is velocity, position, and acceleration. That might completely spelled that. So yeah, so if they're like a question they like to ask is they'll give you some kind of function and an initial condition, and they'll ask you to find like either R of t, v of t, or a of t. So an example here that I have is find R of t. So what's R of t if v of t equals t squared, comma, e to the t, comma, square root of t cubed, right? And we want it so that R of 0 is 690, right? And so you just, how I like to do this is I integrate in each direction. So I know that x prime of t, if I integrate x prime of t, that's just the integral of this guy, which is t squared dt, and that's going to give you 1/3 t cubed plus c. If I take the integral of y prime of t, then that's just the integral of e to the t dt, which is just e to the t plus c. And keep in mind, these are different c's. And then finally you have integral of z prime of t, which is just the integral of root t cubed. I'm just going to rewrite that as this. And take the integral of that. Let's see, you're going to get 5/2. You add 1 there, it's going to be 5/2 up here, right? Plus c. And then you want, so that these are your R of t's. Now this one's supposed to be 6, this one's supposed to be 9, and this one's supposed to be 0, right? Because this is x, this is y, this is z, are corresponding to these values. So if we plug in 0, we should get 6 here. So then c has, so if we plug in t equals 0, this is going to be 0, so c equals 6. So our x of t is going to be 1/3 t cubed plus 6. And then if you plug in t as 0, you're going to get 1 plus c equals 9. So c equals 8. So you have e to the t plus 8. And then here, plug in 0, you get 0, so c is 0. Right. Okay. Yeah, and then you just collect these all into a vector, where this is the x, this is the y, and this is the z. And that's how you do that. Okay, now we can move on to some problems. Let's see. Okay. First problem says we have to find a parametrization of the line tangent. So we want a tangent line to the graph. So we want a tangent line for, oh, and it's, okay, at r of 1, -1, 0, 1. So this is so that means t equals 1. That's what this tells us. And r of t so that's what r of t is, and we want a tangent line. So what I'm thinking is, so r of t, I don't know, some kind of spiral in 3D. And if we want like a tangent line, we need to get a unit tangent vector, well, not a unit tangent vector, just a tangent vector. So something like that, right? And all we have to do is scale them up. But we also, not only do we have to scale him up, but we need to use the principle of moving him to the curve, to the parametrized curve. So if we get, so let's get our tangent vector first. How do we get a tangent vector? We just take r prime of t and plug in t equals 1. So r prime of t is going to be cosine pi t plus or minus t times pi times sine of pi t, comma, sine pi t, plus pi t cosine pi t, and then just 2t, right? And then if we get r prime at 1, let's see, you're going to have cosine of pi, which is -1. And this is going to be minus pi, sine of pi is 0. So that's that. Now, this expression is still the same. Sine of pi is 0. This is going to be pi times cosine pi. Cosine of pi is -1. So -1 times pi is -pi. And then 2t, 2 times 1 is just 2. Right? Okay. So this is the tangent vector, but he is at the origin. So, right, he's pinned at the origin and he's going to this, he's going in this direction. But our curve is right here. It's at this position. Furthermore, we want a line. This is just a vector. So we know that to get a line, we'll call this line L of t. Okay? To get a line, we scale this guy by t. So if we multiply this guy by t, we get -t, -pi t, and then 2t. But we're not done, because this gives us a line, but not where we want. We want him at this point, which is where the position is at. So we're going to add him to -1, 0, 1, and we're going to get -1 minus t minus pi t, and then 1 plus 2t. Right? Yep. Okay, and that's, let's see our answer choices. Yep, I think it's option F. This one is option F, which is correct. Okay, and now let's move on to fall 2024, question 9. They like giving these problems a lot, or like the earlier example where they give you a function, they're like, oh, for this condition to be true, find v of t. So they're telling you that v of t right now is 1, 2t, and 3t squared. And at t equals 0, it passes through 4, -1, and 5. And it wants us to find, like, r of t. What is r of t? So what do we know? When t equals 0, this is its position. So we could rewrite this as r of 0 equals 4 -1, 5. Okay, and then we have to integrate each of these components. So this is the x component, so integral 1 dt. The y component is integral 2t dt. The z component is integral 3t squared dt. Okay, so this is just going to be t plus c. This one is going to be t squared plus c. This one's going to be t cubed plus c. And these c's are different. So this one is going to equal 4. This one's going to equal -1. This one's going to equal 5. And all of these are for when t is equal to 0. Okay? So then that tells us, if we plug in t is equal to 0, that means c equals 4. So you have t plus 4. Okay, when we plug in t equals 0 for the y, you get c equals -1. So you get t squared minus 1. Same thing here, you're going to get t cubed plus 5, right? Yeah. So t, we're looking for t plus 4, t squared minus 1. So d, yeah, d looks like the right answer. Right there. And now last one. This one's a bit different from the previous. So they give you r of t for 2 different particles. So r1 of t is t plus 1, 2t to the half, and then root 2 times t. In the problem, they have it written as 2 to the half, but I'm going to rewrite that as that. Okay, and then r2. So this is the position of the second particle. It's expressed as 2t, t squared plus 1, and t squared minus 2t plus 2 to the half plus 1. And then the question that we're trying to answer is, find the angle between their tangent vectors at their point of collision. So what immediately rings my bells is point of collision and tangent vectors. With angle, I know that I'm going to have to use a dot product because a vector u dot a vector v equals magnitude of u times magnitude of v cosine theta, right? And I could find what that theta is by just rearranging. So we're going to need to find their tangent vectors at some point, but right now we're just going to be concerned about their point of collision. So for them to collide, we need t plus 1 to equal 2s. We're going to call it, because the t of this guy is not the same as this t, so I'm going to call him s. Then we have 2t to the half is equal to, s squared plus 1. And then we have root 2t equals s squared minus 2s plus 2 to the half plus 1. So, this is kind of annoying. I do see something. If t is equal to 1 and s is equal to 1, these two do work, right? If t is 1, you're going to have 1 plus 1, which equals 2. And if s is 1, you have 2 times 1, which is also 2, right? So I'm pretty sure t equals 1 and s equals 1. Let's confirm. If we put it here, 2 times, yep, that's 1, or that's 2, and this is also 2. Then here you're going to get root 2, because root 2 times 1 is root 2. And then here you're going to get 1 minus 2 plus root 2 plus 1. So this cancels with that, and so that does work. So they collide when t is equal to 1 and when s is equal to 1. So we need to evaluate the tangent vectors at these points. So let's find the tangent vectors. So r1 prime of t equals, let's see, that's going to be just 1 comma 2t to the half. That's going to be t to the negative half. Right? Yeah, I'm not being stupid. And then this is just going to be root 2. Okay, and then r2 prime of t is going to be 2 comma 2t comma 2t minus 2. Okay, and then these are constants. And then if we evaluate them at t equals 1 and s equals 1, well, they're both just going to be 1. This is traditionally s. We wrote it as s earlier, but they're both going to be 1. You're going to get 1 comma root 2 for this guy. And then for this guy, you're going to get 2 comma 2 comma 0. Okay, so now if you find their dot product, or I guess r1 prime at valued at 1 dot r2 prime evaluated at 1 is going to equal 2 plus 2 plus 0, which is just 4. Okay. Okay, let's rearrange this equation real quick. So we have the u dot v part. We just did it right here. We got 4. Put it over these guys, the magnitude of them multiplied, and the arc cosine of them is going to equal the angle that we want. Okay, so their magnitudes, this guy is 1 plus 1 plus 2. It's the root of that. And then this guy is going to be 4 plus 4. So this is just root 4, which is just 2. And this one is 8, or root 8, right? So you're going to have, so together this whole expression, so this is magnitude of r1 prime at 1. This is magnitude of r2 prime at 1, right? So what we have right now is arc cosine, their dot product, which is 4, over this guy, so 2, multiplied by this guy, which is root 8. So 2 root 8. We can simplify this, so this is just going to be 2 over root 8, and then 2 over root 8 could simplify even more because you have, inside of the square root, you have 4 times 2, which is 2 over, what do you call it? 2 over 2 root 2. Cancel these. You have 1 over root 2 inside the arc cosine, which if you simplify it a bit more, you're going to get root 2 over 2. So we have arc cosine of root 2 over 2, and we know that that is just pi over 4. Let's see, hopefully I didn't make any, Jesus Christ. yeah, this is C. This is option choice C. Right there. So, yeah. So a little, oh my god, a little bit of a recap. I'll just write this on really quick because this one is kind of a longer one. They gave you R1 of t, and they gave you R2 of t, and they asked for angle, which we're going to denote as theta, between their tangent vectors, so that's just R1 prime of t and R2 prime of t at point of collision. So our whole plan was, first we used what they gave us here to find where they collided, okay? And that's as simple as defining one. So what we did is we just said R of t, and then for this one we said he's a function of s, because this t and this s are not they're not equal parameters. Okay, and then we what do you call it? We found those values of t and s, and we found their tangent vectors. So from these values of t and s, we found r prime at that point, and then R2 prime at that point. And then we use the fact that well, if we're writing it in R terms, R1 dot R2 equals magnitude of R1 times R2 cosine theta. So then our answer is going to lie in this part right here. Arc cosine of R1 dot R2 over magnitude R1 times, magnitude of R1 times the magnitude of R2. And that's how we got our answer. And we evaluated all of these at the points T and S that we found, which is where they collided. So, okay, I hope you guys enjoyed that video. Kind of a more interesting topic, I hope, but tomorrow's video is going to be just part 2 of motion in space, and then after that we're going to be able to do integrals of length. So, yeah, okay. Thank you guys. Please leave suggestions in the comments. Have a great summer.